All right, so we're continuing in to this chapter on entropy and the second law of thermodynamics. There's not just one simple statement of the second law. There's multiple statements of the second law of thermodynamics. So open system, closed system. We're emphasizing using entropy as a property to express it, but you could use another property. That's the start of Thermo 2. It's called exergy, but don't worry about that now. Exergy is another new property. That's in Thermo 2, but we're dealing with entropy. All right, so we pretty well finished it out for a closed system. We need to apply it to an open system. Just in summary, we have the conservation of energy principle. Really, that's, you could call the first law. It's a statement that energy is conserved in all processes. We have an idea of idealized processes and real processes. Well, energy is conserved in all processes, all real processes. There aren't some processes where energy is not conserved. It's always conserved. That's the first law. That's the conservation of energy principle. One other way to look at it is say the only processes that can occur are those for which energy of the system and surroundings is conserved. Think about this. I have the system, I have the surroundings. What else is there? Nothing. It's everything. It's the system plus everything that's not the system called the surroundings. If you have a change in the energy of the system, maybe it goes up, maybe it goes down. And you have the change in the surroundings, maybe it goes up, it goes down, but whatever they do, the sum of those changes have to equal zero. Energy is conserved. We also now have the second law of thermodynamics. It can be expressed as an increase of entropy principle. Second law. So entropy is produced in all actual processes. In idealized processes, some of them we can idealize them to be frictionless, and hence you could think about reversible, no entropy generation. But in all real actual processes, there's entropy production. Some are a lot more entropy production, a lot more harder to reverse. It's more irreversible. The only processes that can occur are those for which the entropy of the system and the surroundings, the sum of that, increases. So the system, change in the entropy of the system plus the change in entropy of the surroundings is equal to sigma, and sigma needs to be greater than or equal to zero. It cannot be negative. Cannot be negative. You cannot have entropy destruction. You can only have, at the best case, very, very, very little, infinitesimally small or negligible amount of entropy production. We put that to zero. But in the real case, it's greater than zero. Okay. So this doesn't say that the entropy of the system always goes up. It could go down, but that's that the surroundings has to be at an increase greater to compensate. The sum of them has to be greater than or equal to zero. Sigma cannot be negative. You talk to a physics major. Oh, yeah, I'm a mechanical engineering major. I just passed thermodynamics. Oh, I'm a physics major. I just passed thermodynamics too. Oh, what book did you use? Let's compare notes. It's like apples and oranges. It's like two different worlds. Yes, in the physics department, they teach thermodynamics. They teach statistical thermodynamics. They deal with the question, what exactly is temperature? You know how long we dealt with that question? Right on through. What is time? What is pressure? Pressure is easy compared to temperature and time. But anyway, statistical thermodynamics has a lot of value, but it's all based on probability, randomness, distributions of where things are and how fast they're going. And often they're based on ideal gas models and molecules. And so anyway, statistical interpretation of entropy is helpful to us as mechanical engineers because, oh, here's a new property. But what does it mean? I tried to say it was described as the molecular disorder of the system. And if you have a higher level of disorder, higher level of randomness, higher level of variability, you have a higher entropy value. Good enough? Most of you are happy? That's nice. But you know, they struggle with exactly how do you express that in an equation form. And they came out with the Boltzmann equation, or Boltzmann did. And so entropy as a property is equal to K log of W. K is the Boltzmann constant. And W is the thermodynamic probability of molecular randomness. This is a great equation in statistical thermodynamics. Professor, are we ever going to use this equation in engineering thermodynamics in this class? No, but you get to see it and tie it together. If you ever talk to your friend that's a physicist or somebody else, oh, I passed the statistical thermodynamics class. There'll be some overlap, but it'll look a lot different. Well, here's Ludwig Boltzmann. These are the years that he lived, 1844 to 1906. The Austrian physicist. If you go to Vienna and you find the graveyard where he's buried, you can find his tombstone. There's a picture of it. It's off of Wikipedia. And what's at the very top up here? You guys think about tattooing things on your arm, your back, your legs. Tattoo your tombstone. There you go. There you go. Chisel it in there. That's his big equation in thermodynamics. So if you just take a look at the images for the grave of Boltzmann, you'll find there's a bunch of images, the bust. Oh, people, they're traveling, they're tourists, they go to Vienna. They take their picture, they put some flowers, and there it is, a close-up, their great equation. And then coming down further, somebody stole your good idea. That's disgusting. That's terrible. I'm embarrassed I even showed that. That was a waste of time, Professor. Oh, cheat sheet. Yeah, they keep lifting up their shirt during the exam. Now we move into the second law for an open system, and we use a control volume to analyze open systems where we could have flow in, mass flow rate in, and mass flow rate exiting, so inlet and exit. When we did an energy balance, that mass took with it enthalpy, didn't it? And now when we do another property, not an enthalpy or energy balance where the enthalpy is being swept in, we do an entropy balance, and it's going to have the entropy in and the entropy exit. So it can lead to a change in the accumulation or the rate of increase in the entropy in the control volume. How can it go up or down? Well, heat transfer bring it in, or heat transfer can take it out. Entropy is transferred with heat. What's the relationship? 1 over T times Q dot. It can come in and out with the mass. In with the mass, out with the mass. And you could have entropy production. True? First clicker question of the day. Sigma dot CV. This term right there. Oh, I forgot. I want to know what are the units for that term, that sigma dot. Is it something like kilowatts, kilowatts per Kelvin, kilowatts per kilogram Kelvin, or kilojoules per kilogram Kelvin? Answer A, B, C, or D. And I just started it now. So you have 30 seconds only. It's going to stop in 30 seconds. What are the units on sigma dot CV? Answer A, B, C, or D. Okay, I guess I only gave you that much time, right? It stopped. So let's take a look here. Now, a lot of people said if it was kilowatts, it'd probably be energy. So good, nobody voted for A, right? Nobody selected A. But we have pretty well the uniform distribution of B, C, and D, which means I don't know as a class. Some know, but some don't know. So this is the right answer, kilowatts per Kelvin. Now, I want one volunteer who selected B and had a lot of confidence to just tell me why they selected B. Why? Okay, you're the volunteer.
Entropy is in kilojoules per Kelvin, and then for rate change, you just multiply by 1/seconds.
Okay.
That becomes kilowatts.
So what he did was he recalled that sigma is kilojoules per Kelvin, and he said when you put the dot on top, that's a 1/, addition to kilojoules per Kelvin, and hence you get kilowatts per Kelvin. Somebody else, your mind worked differently than that. And I know you're out there. You selected the right answer, B. Tell me why. One volunteer. Oh, don't make it so hard. Go ahead. That's the way my brain worked too. What he did was he looked at this equation and he said this term plus minus plus minus plus minus, all of these terms have to have the same units if you're going to sum them up. You can't have something that's meters and meters per second and watts and just add them up. That doesn't make any sense. It's not dimensionally consistent. This equation has to be dimensionally consistent. And so what he does, he says, Q dot, I know what that one is. Kilowatts or watts, true. Temperature, I know what that one is. That's Kelvin. It's got to be consistent. Sigma dot is kilowatts per Kelvin. Thank you very much. So then the general equation, we'll often write it down, but a lot of times some of the terms are consistently zero. How many times do we do a real transient problem? Very rare. So if it's steady state, steady state, steady state, which term gets chunked out? There's no change of the entropy in the system if it's steady state. It's steady, not changing with time. That's the definition. A lot of times you only have one Q dot in, so that summation goes away. Other time you may only have one mass flow rate in, one mass flow rate out. So the equation may boil down to Q dot over TB plus M dot, because if you just have one inflow and one outflow, they're the same magnitude. Drop the subscript I and E for in and exit. And then you'll just have S in minus S exit plus sigma dot CV. So these equations often get simplified greatly from the general statement of the entropy balance equation. Let's solve a problem. The system has 4 heat transfers. Let's find them. They have a Q dot 1, it's showing coming in. They have a Q dot 2, it's shown going in. They have a Q dot 3, its direction is out. Do they report a negative Q dot 3 of negative 650 kilowatts, or is it just 650 kilowatts and the direction on the illustration shows that it's a transfer out? That's what it is. The arrow on the illustration shows that it's an out. Q dot 4 is a positive 250 kilowatts out of the system. Out of the system. So those are the 4. And notice they tell you the boundary temperature at which this heat transfer occurs for 1, the boundary temperature for 2, the boundary temperature for 3, and the boundary temperature for 4. So that you can calculate the entropy transfer with those heat transfers. They have 2 mass transfers. Let's find them. M dot 1 and M dot 2. Both are positive 10 kilograms per second, but the arrow shows an inflow and an outflow, not 2 inflows. You're not getting 20 kilograms in per second. You're getting 10 in over here and 10 out over there. So the arrows are very important. And you have 1 work transfer, W dot. What is the direction of W dot? Positive out. There's only 1 W dot and it's positive out. Determine the mechanical power produced. So I encourage you always to do this. What symbol do I want to use for my answer, and what are my anticipated units on my answer. So what is the symbol that we want for mechanical power? W dot, and the units? Kilowatts. Now, clicker question, a little more challenging. Part B, the rate of entropy production. That's what they want me to calculate. Do they want me to calculate ds CV dt? Do they want me to calculate sigma dot CV? Do they want me to calculate Q dot over TB plus M dot S1 minus S2? Or do they want me to calculate, I can't think of any others, A, B, or C? A, B, or C? All right, so I got it working so it just counts down from 30 and then it stops automatic. So the rate of entropy production, true? That's what they're asking for. And we could write out the second law for a large control volume, and if you just sort of memorize it, it goes the rate of change of entropy in a control volume with respect to time equal to Q dot N divided by the temperature of the boundary coming in, plus the mass flow rate in, entropy in, minus the mass flow rate exit, entropy exit, plus entropy production, rate of entropy production. True? So, which is our best answer for that question? B. Why are two people playing with me? I don't know, but they're playing with me. They're just like, I'm going to show them that I can get a wrong answer if I choose to. This doesn't make any sense. I had even a hard time dreaming it up. It just doesn't make any sense. Now that we know what term that we want to solve for, the rate of entropy production, sigma dot, now what are the anticipated units? Hey, you just asked us that question. True? Kilowatts per Kelvin? Wouldn't those be the anticipated units? So what do is we introduce a control volume. It's already been introduced. It's basically the boundary of the box. And we say, let's do an energy balance, and then we'll do an entropy balance. So if we do an energy balance, all of the ins must equal all of the outs. That's one way of writing an energy balance, true? And so we could have the in of Q dot 1 in plus Q dot 2 in. Are there any other heat transfer ins? 3 and 4 are out. We'll put them on the other side of the equation. Plus mass flow rate in at 1 times its enthalpy at 1. Is there any information about kinetic and potential energy coming in? No, neglect it. Any other ins? How about an out? Q dot 3 is an out. Q dot 4 is an out. M dot 2 H2 is an out. And W dot, what we're looking to solve for, is an out. Can I use that equation to calculate W dot? Sure can. I have to go and I have to get H1. I didn't leave much room, I'm sorry about that, but I have to get H1. It's 3263.9 kilojoules per kilogram, and S1, it's basically steam at 10 bar and 400 degrees C. So that's 7.4651 kilojoules per kilogram Kelvin. And I also have to come over here for saturated vapor at 1 bar. I have to get H2, the enthalpy exiting, 2675.5 kilojoules per kilogram, and S2 equal to 7.3594 kilojoules per kilogram Kelvin. So we can put the two H's in, and you can calculate W dot, and I encourage you to repeat this afterwards. 6234 kilowatts. Make sure you can reproduce that answer. True? So if the energy balance was used to calculate the answer for part A, what balance do we use to calculate the answer for part B? Entropy, the second law. So we have Here, we're just going to modify it. I'll just erase it, make it a little easier. So what do I have is I have entropy, the ins equal to the outs. So Q dot 1 divided by TB1 plus Q dot 2 divided by TB2 plus M dot 1 S1, those in. Then we're going to have outs, Q dot 3 divided by TB3, Q dot 4 divided by TB4 plus M dot 2 S2. Okay, I'm struggling a little bit. Where do I put the W dot? Do I put the W dot on this side as an in or as an out? And then how do I relate, 6,234 kilowatts of power, mechanical power? How much entropy goes with that? How much entropy goes with it? It's like I know that 1,000 kilowatts of heat transfer, I divide that by 800, and that's how I calculate how much entropy goes with 1,000 kilowatts of heat transfer, true? But how do I get how much entropy transfers with W dot? Entropy is only transferred with heat. And you go back and you think to yourself, how does that make sense? Work is an organized energy transfer. Entropy is a measure of disorder. Heat is, on a molecular level, more jiggling, higher energy, higher temperature, hence more disorder, higher entropy. But a heat transfer is a disorganized energy transfer. So W dot doesn't come into the play in the entropy balance equation. It doesn't. All right. I have 2 mass transfers, 4 heat transfers. I have to put in my sigma dot CV. And this is my question. Where do I put it in this equation? Do I put it where its location is A on the left-hand side with the ins, or B on the right-hand side with the outs? You have 30 seconds. Where do I put sigma dot in the entropy balance equation? All right, sorry that 30 seconds goes fast, doesn't it? What can I say? I ask tough questions not to embarrass anybody. You ever had a class like that? Professor knows the answer. They ask a tough question just so they can smirk and say, I've been teaching for 20 years. I know a little more than you. Big deal. Really, really big deal. All right. But how do I describe this? Maybe I go back to the equation, not that one. This equation right here. All right. This is all ins, isn't it? When you have a positive Q dot, that's an in. When you have a negative M dot, what's that mean? An exit. That's an out. So if I would have put, let's Q dot divided by TB, those are all ins. If I would have had any Q dot outs, I would have put a TB there, and I would have put a minus sign in front of it, true? Just like we had a plus in front of the M dots in, a minus in front of. So what's in front of that sigma dot? Plus. It's an in. It's like the principle of entropy, second law, is that it can never be destroyed. It can't be like all of a sudden it just goes away in the system. If it's going out of the system, it has to be transferred with mass or with heat. But how could it be brought into the system? With mass or with heat, or when the system's got a lot of friction, it's being generated. It's an in. It's showing up. It's a showing up. Is there. All right? Makes sense? All right. So let's now say, how am I going to solve for it? Well, you know all the Q's and the T's and the S's, and so I'm just going to say the algebra lets you calculate that the rate of entropy production turns out to be 0.0541 kilowatts per Kelvin. I ask you to repeat that algebra, stick in the numbers, and convince yourself of the final answer. Let's jump on to another problem. All right, liquid water is mixed with superheated vapor. So this is state 1 coming in, that's state 2 coming in, and they're mixed in a well-insulated device called a de-superheater. I did not make the name of that up. And it generates saturated vapor. How many outflows are there? There's only one outflow. What's coming out of there? Saturated vapor. So what came in, look at this temperature and pressure. That's water at 3 bar, 20 degrees C. Do you have enough experience that you could tell me a little bit about the state of that water coming in at 3 bar, 20 degrees C? Subcooled liquid. Take a look at this. Water coming in, 3 bar, 400 degrees C. What do you think? Superheated vapor. Superheated vapor. And what comes out? Saturated vapor. So they're mixing some cold liquid water with something that's superheated, so it turns it into saturated vapor. Don't ask me why they would want to do that, but they do want to do that, and that's how they do it. All right. Determine the mass flow rate of the superheated vapor. So I asked a clicker question for part A. Are they asking me to calculate M.1, M.2, or M.3? And yes, you only have 30 seconds to answer this question. Choice A, B, or C. For part A, they say mass flow rate of superheated vapor. Are they asking me to calculate M.1, M.2, or M.3? All right, as a class, you have redeemed yourself. You're teachable. Well, except for 3. But that's okay. The thumb is big. You intended to push B, and you just slipped over and hit C. I know it. It happens all the time. But there you go. So that's what you're asked to solve for part A. You're asked to solve for M.2. Okay. And they give you the units, kilograms per second. The rate of entropy production in the de-superheater, what symbol? Sigma dot CV. Rate of entropy production. That's that. Okay. How are we going to solve for the mass flow rate 2? Do we know the mass flow rate at 1? Yeah. Mass flow rate at 2 is unknown. How about mass flow rate at 3? Unknown. Sometimes you have to go back and you have to do a mass balance, then an energy balance, then an entropy balance. This is one of those cases. If you do the mass balance, M-A-S-S, I can spell, you get the M.1 plus M.2 summed equal to M.3. Not a very exciting equation, but it's needed. Because when you write the energy balance, you would have an extra unknown. You don't know M.2, you don't know M.3, so you would be stuck. And with the mass balance, now you have 2 equations, 2 unknowns, and you can solve for them. So let's write down the energy balance. So what's an in? M.1 in, bringing with it enthalpy 1. Plus M.2, bringing with it enthalpy 2. It's an out with sums. That's the only ins. Let's go to the outs. M.3, enthalpy 3. That's it. That's our energy balance. So what we do is we say, I know what M.3 is. It's equal to M.1 plus M.2. I'll do just a little bit of algebra, and I'll get an equation for M.2. M.1 times a ratio of differences in enthalpy, H3 minus H1, H2 minus H3. At state 1, can I get H1? Sure, you can go get H1, 83.96 kilojoules per kilogram. Can I get S1? I'm going to need it while I'm in the tables. Let me get S1, 0.2966 kilojoules per kilogram Kelvin. Can I get H2? Yeah, it's superheated vapor, 3275.0 kilojoules per kilogram. How about S2? Sure, right next to it, 8.0330 kilojoules per kilogram Kelvin. Then I come over here. Can I get H3. Sure, H3 is 2725.3. Don't have room for units. S3 equal to 6.9919. I can fit the units for this one. Kilojoules per kilogram Kelvin. So when you substitute the enthalpies, you find mass flow rate at 2 is equal to 0.961 kilograms per second. In the interest of time, I encourage you to reproduce that at home. Now, for part B, the rate of entropy production, you can write the second law where you have ins equal to the outs. What's flowing in equals to what flows out. Maybe you write it like this. Mass flow rate 1, S1, plus mass flow rate 2, S2, plus mass flow rate 3, S3 is out. Should I put the sigma dot CV there or the sigma dot CV there? I'll ask a clicker question. A or B? Where do I put what I'm asked to calculate? The answer for part B, the rate of entropy production. I'm writing the second law, sum of ins equal to the sum of outs. Should I put sigma dot CV there? Answer A. Or there? Answer B. All right. I have the same two playing with me. They're just playing. He wants some wrong answers. Here you go. You got some wrong answers. Thank you very much. So there's where we put it. It's an in. It's a production. Okay. Now, what we can do is we can solve for what the entropy production is. M dot 3 times S3 minus M dot 1 S1 minus M dot 2 S2. Notice you have to sweep out everything that you brought in plus what was produced. That's one way of looking at that equation. Try to read your engineering equations. I know it's a little challenging when they're brand new to you, but hopefully you can think through them. 0.339 kilowatts per Kelvin. Good? Ready to move on? Steam at 20 bar, 400 degrees C is 60 meters per second, enters an insulated turbine. So here's our turbine. It's insulated, so Q dot 0. You have inflow at state 1. You have the pressure at 1 of 20 bar. You have the temperature 1 of 400 degrees C. You have the velocity 1 of 60 meters per second. The steam flows out at state 2. You have the pressure at 2 equal to 3 bar. The temperature at 2 is not known, but the velocity at 2 is 90 meters per second. The work developed per kilogram of steam flowing is claimed to be, so what they have is a shaft and it produces some power, W dot out of the turbine. But if you divide that by M dot, the mass flow rate of the steam going through the turbine, then we have lowercase WT, the specific work of the turbine. That has units of kilojoules per kilogram. So they're telling us the power out is 520 kilojoules per kilogram. Or you could think of kilowatts per kilogram per second, something like that. Can that claim be correct? This is the value of the second law. It could conserve energy, but it could break the second law and be not unrealizable. It could not be possible. So here somebody says, is it possible that you could produce 520 kilojoules per kilogram? And then once you've done that, take a look at 620. Well, what you do is you say, let's go ahead and write the first law, energy balance. Energy balance. I'll put it over here. So for the energy balance, we're going to have the exit enthalpy plus the exit kinetic energy is equal to the inlet enthalpy plus the inlet kinetic energy, that's V1, minus the work that went out in the turbine. There's a number of ways you could write it, but it's written that way. Okay. So I'm looking at the energy. It's like, okay, if they told me to try 520, They gave me the velocity in. I think I can get the enthalpy in. I just go to the steam tables and I can get H1 for that, and it's 3247.6 kilojoules per kilogram, and S1 is 7.1271 kilojoules per kilogram Kelvin. So the pressure and the temperature allowed me to fix the state and get the other properties. And then they told me, did they tell me V2? So the only thing I really don't know is H2. So basically, I'll use that equation to calculate H2. And when I use that equation to calculate H2, it's going to be H1 plus 1/2 V1 squared minus V2 squared minus the reported work of the turbine. Now, the only thing that you have to remember is units. Where do a lot of students make errors with this type of problem in units? That's right. That's 1,000 meters squared per second squared is 1 kilojoule per kilogram. That's a unit conversion that you need to use. Anyway, we come in and we can predict H2. The H2 turns out to be 2725.35 kilojoules per kilogram. This and this, not that, the pressure and enthalpy fix the state. And what I can do with a little bit of work is I can calculate S2. It just how happens that it happens to be saturated vapor, and so this is S of G at 3 bar, 6.9919 kilojoules per kilogram Kelvin. We go to the entropy balance, and we want to check. We want to see what's sigma dot for this problem. So what we find is that the sigma dot is equal to the mass flow rate, entropy exit minus entropy inlet. A little bit of algebra right there, but you get that for the second law. We stick in our numbers, but you hardly even have to stick it in. Here, just do this. Divide this by m dot, and now it's equal to. Look at the value of S. Did it go up from 1 to 2 or go down from 1 to 2? How could it have gone down? There is no entropy destruction. So what about this claim? It's not true. So for this claim right here, it's impossible. You say that it violates the second law of thermodynamics, because to be possible, it would have to destroy entropy, and that's impossible. Sigma dot here, sigma dot per m dot is calculated to be negative 0.135 or something kilowatts kilojoules per kilogram Kelvin. Oh boy, I got to work those out. Yeah, I think that's right. Yeah, that's it. All right. So now let's take a look at 620 kilojoules per kilogram. Do you think that's possible? How about we just guess? Clicker question is a guess. Do you think that this is A, it's possible, or B, impossible? Just say, I think it's possible. Answer A. Did it already? No, you got 15 seconds to guess. We said getting 520 kilojoules per kilogram out is impossible. How about 620 kilojoules per kilogram? All right. Well, a lot of times when they ask A and B, and you think, oh, one's going to be possible, one's going to be impossible. But look at the trend. Would it be better if you got 620 out versus 520 out? Which would you like if you're selling power? I would like 620. That's the challenge for mechanical engineers. Turn steam power into shaft power. And that's harder to turn it to 620. So guess what? There's no way. There's no way. It is, look at that. The probability of getting that 50-50 is incredible. So the logic is there. So what you do is you go back and you say, you know what, I have to redo this, but you know, for the next H2, for the new H2, I find it has to be even lower. It has to be 2635.3. And then I find, oh, now it's going to have a quality at 2. The quality is 0.958. Where was it before? It was saturated vapor. Now it's in the two-phase region. And the S is lower. It's not possible. It would have greater entropy destruction. So let me try and do this. Somebody says, what is the maximum work developed possible by that steam going from this through the turbine? Well, let me do this. Let me show you on a temperature entropy diagram. Here's our dome. Here's a line of high pressure. And here's a line of lower pressure. And we started out at 20 bar and 400 degrees C. That was state 1. And somebody said, if you, I didn't draw it too well. Let me push one out a little further. There's state 1. All right? Now, somebody said, if I went here, I would actually have a decrease in the entropy. And if I went here, I'd even have a greater decrease in the entropy. Both are bad. Both are impossible, I should say. So what happens is if it's still a well-insulated turbine, the best you can do is straight down. And when you go straight down in this problem, you'll have slightly superheated steam at the exit. Okay? So what you do is you set it up such that you have the pressure 1, the temperature 1 are fixed, so you get H1 and S1. Then you come over here, the pressure 2 is fixed at a lower pressure. You basically say the best I can do is if sigma dot per m dot's equal to 0. If that's true, then S2 is equal to S1. See? If that's true, then S2 is equal to S1. It's not an isothermal expansion through the turbine. It's not an isenthalpic expansion through the turbine. A property known as entropy is constant. It's isentropic. S equal constant. It's an isentropic expansion through the turbine. So this then sets S2 is equal to S1, which was 7.1271 at, what, 3 bar? I forgot the lower pressure. These two fix, hence you can get the property H2, and that H2 is H2S. It's the isentropic value at state 2 from expanding from state 1. So a lot of times we'll put H2S. So this would be the 2S right there, state 2S. Now, when you do that, what you find with a little bit of work is that the work out of the turbine maximum is going to be 465 kilojoules per kilogram. Oh, you can always get less. You could put 2 actual here or 2 actual there. There would be some irreversibilities, and you wouldn't develop as much power out. The best you can do is straight down isentropic expansion. Over here, not possible. Not possible. Over here, it's not as efficient, but it's still possible. So that's showing you on a TS diagram. Thank you for your attention. We'll see you Wednesday.